triple frequency currents in the power transformer. We want sinusoidal voltages in each one of the coils of a transformer. But that voltage will be induced in the coil by a flux according to Faraday's law. That means that if the induced voltage E is to be a sinusoidal function of time, the flux needs to be also a sinusoidal function of time. But how do we create a flux that is sinusoidally changing with time? That flux, sinusoidal flux, as we saw, induces this sinusoidal voltage. But that flux is induced by the current in one or more of the coils of the transformer, according to the magnetization curve. There are two curves actually. One, this one, when the flux is increasing, and this other curve when the flux is decreasing. Given the curve and the sinusoidal flux, we can reconstruct point by point the necessary current to create that sinusoidal flux. And look at the shape of that magnetization current. It is not sinusoidal. Actually, it looks like a children's costume for a Halloween ghost. This is a simplified view of that magnetization current. It does indeed look like one of those children's costumes for Halloween ghosts. If we apply Fourier to that function of time, we realize that that is the sum of several sinusoidal functions of time. So like this one plus this one. In reality, the actual curve is the sum of many more sinusoidal functions of decreasing amplitude and increasing frequency, but these two are the principal ones, the main ones, the most important, and the analysis will be restricted in our video to only those two currents. We say the magnetization current actually is the sum of two sinusoidal currents, one that is a 60 Hertz current, the red one, the fundamental frequency one, and another one, the green one, that is oscillating 3 times as fast as the fundamental one. We call this a triple frequency current of magnetization. That is one. And these are the two components of that magnetization current. In short, to create a sinusoidal flux, we need to have a sinusoidal current of 60 Hertz, this one, which we call the fundamental component of the magnetization current, and a triple frequency current, this one, that we call the triple frequency component of the magnetization current. 60 Hertz and 180 Hertz correspondingly in Canada. In Europe, those would be 50 Hertz and 150 Hertz. Let's summarize for phase A. We say, to have a sinusoidal induced voltage in the coils, we need a sinusoidal magnetic flux. But for a flux that is changing sinusoidally with time, we need two currents in the primary. Observe the asterisk. A 60 Hertz current, also known as the fundamental component of the magnetization current, and a 180 Hertz current, the triple frequency component. As I said before, 2 is an approximation. What happens if there is no triple frequency in the magnetization current? Could be we filtered it out, or we wired the transformer in a way that prohibits triple frequency currents from circulating. If that is so, if we have no triple frequency in the magnetization current, then the flux will be distorted and the induced voltage will not be sinusoidal anymore. The induced voltage will look like this. It's not a sine. But interestingly enough, if we apply Fourier to that induced voltage now, which is seen, by the way, by the customer, we realize that voltage is the sum of two sinusoidal voltages. One voltage of 60 Hertz, this one, and one voltage of 180 Hertz. That is, now we do not have triple frequency in the magnetization current, but the price we pay is that now we have a triple frequency voltage, which is visible by the client, by the customer, and that is not good and not acceptable. Observe the situation. In this simplified diagram of a transformer, we're applying a magnetization current, and that has to be like this one. It has a 60 Hz component and a 180 Hz component as well. And if we do so, the flux is sinusoidal, and the induced voltage in every coil, including the secondary, will be sinusoidal, and the customer will be happy. If, for some reason, we manage to filter out the triple frequency of the magnetization current and we apply a magnetization current that is purely sinusoidal, the flux will not be sinusoidal, and the induced voltage now will have triple frequency voltage waves in it, and the customer will be very unhappy, and he'll make sure to make you unhappy. In a three-phase system, I have depicted the magnetization current of each one of the phases, in black for phase A, in red for phase B, and in green for phase C. Each one, of course, has a fundamental component and a triple frequency component, but we better see them separately in three different graphics. For phase A, the fundamental component in green and the triple frequency component in red are depicted here, and then for phase B and for phase C. Do you notice a fundamental component of each one of them is actually separated from the fundamental of the previous phase by 120 degrees? The green one? Absolutely. But what happens with the triple frequency component of each one of the currents? Well, you say nothing happens. Actually, the triple frequency component of phase A, of phase B, and of phase C have the same magnitude and the same phase. Interesting. Again, looking only at the triple frequency component for phase A, for phase B, and for phase C. Those three currents have the same magnitude and the same phase.